Hello, and I would like to perform a calculation, which is a really interesting Physics 1 problem, calculus based, where we have to figure out what is the minimum height of a roller coaster car for its first hill in order for it to achieve a vertical circular loop of radius capital R. And we want to know what the H minimum, the minimum height of the first hill, as a rational multiple of R. So that is, as some nice fraction or decimal, multiple of R. So, most roller coaster loops in real theme parks are actually teardrop shaped, but let's assume this is circularly shaped for greater ease of calculation. Also, we're going to assume no friction, so in reality, real roller coaster hills actually need to be taller than what's described here. But in order to achieve this problem, I first think we should use the conservation of energy. Because given we don't know what the slope of this hill is, and given that all that really matters is that we're going to conserve mechanical energy in the absence of friction, conservation of energy will be the way to go. So let's use the conservation of mechanical energy. Okay. So the conservation of mechanical energy should say the following. And in fact, by the way, I think the 2 points that are of greatest interest are going to be this point up here at the top. Let's call this 1, or we could just say top. And then this point right here, so what we could say is point 2 is on the loop. Now, the loop point is actually at the top of the loop. Okay, but you can imagine that the gravitational potential energy at the top of the hill becomes all kinetic energy at the bottom of this loop, but then it becomes some kinetic and some potential energy at the top of this loop. So the conservation of mechanical energy is most generally written that the mechanical energy initial is equal to the mechanical energy final. But with that, we can still also say that more particularly, it's kinetic energy plus potential energy. And in this case, it's gravitational potential energy. So let's call this kinetic energy initial at the top. Remember, that's position 1. Plus gravitational potential energy initial at the top is equal to kinetic energy final at the loop top, so let's call that loop, plus gravitational potential energy final at the top of the loop. Okay, so now let's put in expressions for these things. Let's assume this is mass m for the car, and let's also be careful about how we write everything in here. So this is 1/2 little m v initial squared plus mgh initial is equal to, and that's going to be 1/2 mv, let's call it final squared, because that's at the top of the loop, plus mgh final. Okay, so now let's walk through this. So first things first, we can get rid of the 1/2 by multiplying everything by 2. This is often what we do in conservation of energy problems. Secondly, notice that mass is common to all these terms. So if we divided the entire equation through by mass, the masses would indeed cancel. Next, let's think about what the initial velocity is. So we're told that it starts from rest. So that means the initial velocity is going to be 0. So that means this entire term right here is equal to 0 because this is 0. And then what's H initial? Well, H initial, we're going to call that H min. So the minimum height to just barely make it through this circular roller coaster loop. Next, V final. We don't really know what that is, but we'll have to investigate that. So I'll just put a note here, investigate. And then finally, what is going to be H final? Now let's look carefully. So H final here is the final height to barely make it through this loop. And that I think is going to be 2 capital R, 2 radii. So it's 2 capital R. So let's rewrite this equation in a much more condensed form. Okay? So the conservation of energy equation should become, multiply the equation through by 2, and this first term went away. So we just have 2g h minimum is equal to, let's see, V final squared plus 2 times G times 2R. Okay, so we can get H minimum in terms of this V final and in terms of the radii if we divide by 2G. So H minimum is equal to V final squared plus, and let's be careful what this is. This is 2G times 2R, so that's 4GR all over 2G. Now, of course, I could simplify the second term here, but the first term would remain a fraction. So that's going to be the following. So this is going to be V final squared over 2G. So plus 4GR divided by 2G. 4 over 2 is 2. G divided by G cancels. We're separating this fraction over its addition in the numerator. So that should be 2R. Okay, now we're getting somewhere. Notice we have the minimum height completely in terms of R and G and this V final squared. So let's see if we can say something about this V final. So remember here I said we need to investigate this V final. So let's in fact investigate. If I approximate this portion up here with this sketch, so here's position 2. It's approximated with a sketch. And this is the object as it's moving through this loop. I think that this object moving through the loop is going to have the following forces on it. It's going to have its own weight, and it's going to have some normal force on it from the track. So that's the normal force. Now imagine this. As we go upward, the weight and the normal force are more and more so directed toward the center of this circle. So this is the center of the circle that we're talking about. We know in order to maintain circular motion, we have to have a centripetal force. We have to have a force that keeps us in circular motion because we're directionally accelerating. That's what it means to have a centripetal force. Furthermore, since we're directionally accelerating, we know that the centripetal force has to be maintained. So we can say that if this is the radial direction towards the center of the circle down here, that Newton's second law reminds us that the sum of the forces in the radial direction is going to be the normal force plus mg equals the centripetal force, which is the net force in circular motion. That's mv squared over r. Okay? And by the way, this v squared is v final that we've been talking about here. So it's the v final at the top of the loop. Now notice, again, the normal force gets greater and greater in the direction of interest, that is towards the center of the circle, especially as we get towards the top. And the weight is also more in the direction of interest. So if we want to barely make it through the loop, barely making it through the loop will actually have the normal force going to 0 newtons. In other words, we will just barely make it through the loop. This will be the minimum velocity that at that one moment we don't have any normal force. So we're only going to have mg equals mv squared over r. And the v squared is that v final that we've been talking about. And notice that these masses would also cancel when we equate these. So look at this. We can actually get v final squared. So we can then, from the second part here, the centripetal part, so from the centripetal part, we can express v final squared as g times r. And notice now this can be inserted into this v final squared. Okay, so let's go ahead and put that in. Oh, and then one more thing. I'm sorry. This r here is, in general, we typically use lowercase r for centripetal force. But let's call this capital R, because capital R is the radius of the loop, which indeed is the radius of interest. So, sorry about that, but I'm just going to put in G capital R. So this is G capital R over 2G plus 2R. And look at how this works out beautifully. The G's cancel. R over 2 is 1/2 R. But 2R is 4/2 R. So this is r over 2 plus 4r over 2. And the amazing result we get is 5r over 2. This is a very unique result. Notice that many physics students actually remember this result semesters after. That if you're going to build a roller coaster hill to be sufficiently large to make it through a circular loop, you should not build it the same height as the roller coaster loop. Because if you do, then it won't make it fast enough. It turns out, sure, you can imagine that the object will start off with 0 velocity here, it'll make it to 0 velocity here, but then it'll just drop off the loop. It won't make it. Notice also if you start a little bit higher, you still won't make it. It's got to be actually a half radius, height larger, to have the object high enough that it, because of the centripetal force, it'll actually make it through the loop. So I want to show a proof of this using a simulation by Professor Walter Fend. So stay tuned in just a moment. So here is a new simulation by Professor Walter Fend. And I really want to thank him for his wonderful physics apps. So you can check this website out. Okay. So here's the main URL, at least in English. Okay. So here we go. Here is a ball and here is a loop. Okay. So what we can do is we can slow this motion down to 5 times or 50 times as long as it would usually take. Notice we can set the radius and the initial height of the ball. The gravitational acceleration is 9.81. Okay, so it's actually not even going to matter what g is, because if you recall, the expression is going to be the same no matter what g is. All that matters is the height and the radius of the loop. And the mass isn't even going to matter. So we'll investigate those later. But let's first have a look at the weight and the contact force. So what Professor Walter Fend calls weight and contact force is going to be the mg and the normal force. Okay. Now let's see. The radius is 0.5 and initial height is 0.8. So let's just go ahead and start this up. So the weight is down, the normal force is perpendicular to the motion, but you'll notice the object, it doesn't make it. It doesn't make it all the way around. So let's reset. So the more sort of naive way is to say, oh, just set the object to the same height as the height of the loop. In other words, 2r, 2 radii. So let's change this to 1.0 meters. Okay? let's watch the object. It should make it to 0 velocity at the top, but then I don't think it's going to have enough velocity to finish the loop. It doesn't even really make it to the top per se, and that's because it's not maintaining enough velocity to make it in circular motion. So let's reset again. Notice if we go just a little bit higher is not going to be enough. So 1.1. Notice now we've made the incline larger, so it starts off at a higher height. Still not enough. We shouldn't just guess. So instead, let's bring out our calculator and let's say, okay, if we have 5 halves, 5 divided by 2, that should be the same thing as 2.5. 2.5 times 0.5 should be 1.25. So 1.25 is the initial minimum height. So the object should hopefully barely make it through this loop. If we go 1.25, 1.5 radii. So let's go ahead and see what happens. So the object barely does make it through this loop. Okay? Of course, if we set to higher heights, maybe 1.5, the object should still make it through this loop, but it should also have larger velocity even as it makes it through this loop. Okay? And hopefully you saw there that the normal force was non-zero. So let's reset and let's go through some of those again. So I think we started with 0.8. Let's show the velocity here, and this time let's show the tangential and radial force. So notice the velocity is in the direction of motion, and the tangential force is the force that's along the direction of motion. But notice the radial force is the centripetal force. So notice that when the object came from a height of 0.8 meters, there was no, let me reset this. There was no radial force at first. There was only a tangential force, which caused the velocity to grow. When we started going through this loop, notice that what's going to happen is the tangential force is still going to be in the direction of the velocity the whole time, but there's going to be a centripetal force. So now it's there once we're on the surface of the loop. Notice that the centripetal force, which is the radial force, needs to be maintained enough so that it does not get to 0. If the centripetal force gets to 0, we're no longer in circular motion and the object should actually fall off the loop. And that's what we do observe here. Okay? So we observe that the object does indeed fall off the loop. Now let's go back to the 2R solution, and that's not really a solution, it's 1 meter high. Notice that, again, the tangential force is in the direction of the velocity. The object makes it higher this time, the centripetal force still goes to 0, and notice that it falls off. So, our minimum, we said from our calculation, was 1.25 meters. So, this is going to be just high enough. Notice that there's going to be a tangential force and then in the direction of the velocity. Whereas the tangential force when we go up the roller coaster loop is in the opposite direction of the velocity, but the tangential force is in the direction of the velocity when we go down the loop. So that causes the object to speed up until we reach the bottom of the loop. Now I'll slow it down. So the tangential force is in the opposite direction as we ascend of the velocity. The centripetal force is getting less because the velocity is getting less. But we have just enough velocity so that the centripetal force is equal to the weight and only equal to the weight, not the normal force. At the top of the loop, the velocity is maintained. It's tangent to the circle, and then notice that the object then will start to gain velocity. It'll go faster as it goes down the other side of the loop. Gravity is doing positive work, and the object will proceed out of the loop. Okay? And then, of course, if we go even higher heights, we should be able to just get the object through the loop at a faster velocity than what is the minimum. By the way, part of the reason real roller coaster hills are so high is not just because of loops, but also because of friction. So we didn't include friction in this analysis. So let's see if we go back to our 1.25 meter barely makes it through solution. Let's look at the total force, and let's also see if it depends upon what g is. Let's do about 1.67. Let's imagine that we're on the moon. Well, if we're on the moon, it should still work. Now, the object's going to accelerate very slowly, but it is going to still accelerate, and it still should make it through the loop. Okay? So notice black is the total force now, the sum of the tangential and the centripetal, but the object still makes it through the loop, even though it's, sort of takes a long time to accelerate. Let's go back to good old Earth value, 9.81. And let's now change the mass. Let's make this, I don't know, twice as large. So I can't do that. Let me go ahead and see if I can make this half. Okay, so I can make it half as large. Okay. And even though I make it half as large, the object should still make it through the loop because m, it's independent of m. M is not in our final analysis equation for the minimum height. Okay, so I hope this all makes sense to you why this is the minimum height for a hill to make a roller coaster car through a loop. Thank you all very much for your attention. And if you like this content, please smash that like button and please subscribe to the channel in order to grow the channel. And please share this amongst your social network. Thank you for watching High Peak Education. I will see you in the next video.